All right, welcome back, everyone. This lecture is using MaBoSS, which is similar to Tellurium, those ordinary differential equations you're embedding to cells. But in this case, we're going to use a Boolean stochastic network, which is a simpler representation of what is going on inside the cell. Again, this is being live streamed, recorded, and distributed. And my name is Pedro Cenci dal Castel. Okay, so what are Boolean network models? Boolean network models represent cells, states, and protein states as a true or false statement. So, for example, if you're modeling a gene, if the gene is active, it has value true. If the gene is inactive, it has value false. So it's a binary thing, and there is nothing in between. There are some ways of creating stuff in between 0 and 1, but each node of the network has just 0 and 1 value, true and false. The objects of these network are the nodes. You can have nodes represent proteins, cell states, cell behaviors, genes, so on. And the states of the nodes, which are true and false, they change stochastically. So there are rules that you can set, but ultimately they sample from a random distribution whether they're going to turn on or off. They can be very suitable for gene regulatory networks where certain genes are on or off. It can be an effective simplification. And protein signaling if a certain signal is present or absent. However, you do need to be careful that sometimes it is very important that an activation level, if an activation level is important, representing with a Boolean stochastic network has drawbacks. There are some ways you can approximate uh, response to graded response to stimuli. For example, you can use Hill functions to define rates that depend on the concentration of certain chemical outside the cell. And you can define extra nodes per object, per protein, or extra nodes per gene, so that you have a cascade of reactions and each node represents one level of activation of that object. But it has limitations. Let me explain how a simple deterministic Boolean network functions, and then I think we will be ready for our first exercise. So a Boolean network is a network of nodes. So it's um, you can have as many nodes as you want, and they can be all connected and the connections represent certain interactions. In this case here, we have G1, G2, and G3 nodes, and the pointed arrows represent a stimulation or an upregulation interaction, where, for example, if G2 is true and G1 is false, in the next step of this deterministic Boolean network, G1 will go from false to true. The blunt arrowhead or the T arrow represents an inhibition. So, for example, if G1 is true, G3 goes to false if G3 is true. So with these interactions, you can write a state table where if you have a current sequence of state nodes or node states, you can find what is the next state of the network. Also, when you have multiple interactions arriving at the same node, you have to decide how you are going to define the interaction between these multiple interactions. For example, if G1 is true and G2 is false and you have a pointed arrow, you might say, okay, G2 goes up. But if I have multiple upregulation arrows going to G2, it is different to say I want both G1 and G3 to be true, to be positive, so that G2 goes up. This is different than saying I need either G1 or G3. So we use these and or operators to make it clear what is the interaction between these two arrows. Also, the blunt arrow can have two meanings as well. And these meanings you have to define. And you can represent all these meanings in MaBoSS. One of these meanings is, for example, if G1 is true and G3 is true, of course, G3 goes to false, goes down. But if G1 is down and G3 is down, does G3 go up? This is ambiguous if you just have this blunt arrow. So you could have, if G1 is false, G3 goes up naturally, or you could have, if G1 is false, nothing happens to G3. So the conceptual representation, which is the arrow and nodes, sometimes doesn't tell you everything you need to implement this network in a mathematical model. In the case of a deterministic Boolean network, you could solve it, you solve it synchronously, so all the nodes get updated per step. This is also true for the Boolean stochastic network. The difference from a deterministic Boolean stochastic network to from a deterministic to a stochastic Boolean network is the stochastic has a rate of going up and a rate of going down. While in the deterministic, if a given condition is true, the change of state in the node is deterministic. It's going to happen in the next step, or it is not going to happen in the next step. While in the stochastic Boolean network, you could have leakage. For example, even if the logic for example, inhibition is true, G3 and G3 is false, G3 might have a probability of leaking, so G3 would go up for a while and then go back down, and you can set the probabilities for these transitions. So in a deterministic network, you can draw the transition graph from one state to the other, while in a Boolean stochastic network, you could have something like this guy jumping straight here with a certain probability, if you allow that to happen. So you could have all nodes connected, but the logics would determine what are the most likely outcomes. So why would we use stochastic Boolean networks instead of ordinary differential equation systems? There are a couple of reasons. First, MaBoSS tends to be faster than ordinary differential equation solvers. And often in the literature, you will not have all the information you need to calibrate an ordinary differential equation model. For example, sometimes an experiment will just tell you whether the cell is glowing under fluorescence or not, with not much information about the level of the protein inside. If that's the case, and you lack the information of the level of the protein, how long does it take to, like, what is the production rate of the protein? What is the decay rate of the protein? You don't have all this information. You could approach the problem with a simple Boolean stochastic network first, and then see what happens. See if you need to represent the rate of production and rate of decay to reproduce the experimental results before you attempt a more complicated ordinary differential approach. Also, sometimes a molecule goes up very, very fast and goes down very, very fast. I think this is the case where Boolean stochastic networks are most suitable. If things happen very, very fast, for example, with kinases or those very small signaling proteins inside the cell that get phosphorylated and dephosphorylated. These processes are very fast. I think you could get away with using Boolean stochastic network for those. So for our CC3D plus MaBoSS exercise, we are going to change our previously Tellurium version of delta notch. We'll substitute that with a MaBoSS model. So it's a very simple exercise. We already have the setup and the understanding of the delta notch simulation. And let me see if I can run the video here. So basically, the delta notch simulation is a contact inhibition simulation or like a contact activation slash inhibition simulation. You can have both. Where depending on the neighbors, depending on the level, the protein expression level of your neighbors, the cell in the middle has a certain fate. It could be a notch expressing cell or a delta expressing cell. In Tellurium, we use rate equations for that. In the case of MaBoSS, we're going to use nodes and transitions, stochastic transitions. And this is how the code looks like. You have in CompuCell3D, you are already familiar with looping over cells, looping over neighbors of cells. And using MaBoSS, we're going to use some pieces of code that you have available in to edit snippets. For example, getting the state of a node of the cell, defining a MaBoSS parameter, so passing the value of some value that you have in the CompuCell level, in the tissue level, pass that value inside the Boolean stochastic network, and integrate all MaBoSS simulations so that all cells that have an attached MaBoSS simulation integrate the MaBoSS, time step this MaBoSS model. Let's take a look on how to define a node and define the initial conditions and parameters. So MaBoSS is written in C, and the specification is also in C. So there is this annoyance of curly brackets and semicolons. Every line has to end in a semicolon, and nodes have to open and close with curly brackets. Okay. There are two files. One is the network specification file, and the other one is the configuration file. The network specification is where you have the nodes and the rules for state transition. And the configuration file is where you have the initial condition of the nodes, the value of the rates, and other settings. You could have MaBoSS, for example, do ensemble averaging, and you would set it up on the configuration file. This is the link for the documentation, maboss.curie.fr. And let's take a look at the syntax, how it looks like. You have the name of the node, so node A, node B, and node C. And inside you have your rules. So you have a rule for going up, rate underscore up. This name is proper of MaBoSS. So you have to use the variable rate underscore up. It can't be anything else. If you say rate up without an underscore, that's something MaBoSS will not recognize as a rule. So rate up and rate down for each of the nodes. And then you have a logic statement for each of these. You could also not have a logic statement, okay? You could have rate up equals 1, and that's it. Done. But in C, also in Python, you can write logic statements on the right-hand side of an equality. In this case, you have a logic. It's something that will either be true or false. So it's basically asking if the node C is up and the node B is down. So if you have C equals up and C equals down, this logic evaluates to 1. And if this logic evaluates to 1, which is this question mark, is evaluating this logic, this is what happens when the logic is 1. Your rate up is equal to this first symbol, this first value. So it could be either 0 or 1. And it will be the second value otherwise. Okay? So this is evaluating. The question mark is evaluating. And the column is an else statement. So if the logic is true, you use the first value. If the logic is false, you use the second value. All right. Let's remember quickly how the delta notch model works. So you have cells with different expressions of delta and notch, and they have their neighbors, which also can have different levels of delta and notch. Delta in a neighbor induces notch on yourself. So if a cell has a neighbor with delta, the delta of that neighbor is inducing notch on that cell. And notch inside the cell, so self notch, inhibits self delta. So this creates a situation where cells try to segregate who is expressing delta and who is expressing notch. Of course, it depends on the parameters you set. You could have cells with notch isolated or cells with delta isolated, depending on the parameters of the model. And you can achieve all sorts of patterns depending on the parameters of this model. So our first exercise is just to get your delta notch simulation. We are going to start from the Tellurium implementation. Although I also have the MaBoSS implementation if you want to skip the exercise. It's on the drive folder. So if you don't have the Tellurium implementation, you can get it either in the chat. You should have a Tellurium model for the delta notch, which looks way less scary than a MaBoSS implementation for sure. And make sure you can run it. This one I have delta. Yeah, sorry for that, everyone. So you should have something like this. Okay, let's proceed. And so here's what I'm going to do. I'm going to explain how the exercise is going to work. And then instead of having you following step by step what the implementation, I'm going to first explain each step, and then I'm going to show you a summary slide of everything you have to do, which is this slide over here. It contains all the pieces of code exactly the way you want to implement them, and you can copy and paste from here. And I don't know why it's not highlighted, the syntax, but that's something I will fix eventually. And the instructions are all here as well. Okay, so I will start by explaining each step, and then I'll show you that slide, and that's when we're going to stop, and I'm going to stop, and then you'll follow the steps one by one at your time. Okay, so let's take a look at the delta notch implementation in MaBoSS. We have node notch and node delta. Okay, that's necessary. We have the two nodes for each cell. And then we have a logic for notch and a logic for delta. You can separate the logic from the rate. Okay, you don't need to write rate up equals and then you write a statement and then evaluate. So you can have different logics. You can have logic 1, logic 2, logic 3. This is what happens if logic 1 is positive, if logic 1 and 2 are true, if logic 1, 2 are true, but logic 3 is false. What happens, and then you cascade all the, you can do whatever you want using C syntax. Okay. In this case, we have just one logic for each. This is a very simple representation. So here the logic for notch is if DAVG, this is the average delta around the cell. So this is a parameter. If it is a parameter, it has this symbol, the dollar sign before, because it's not a node. If I do not have the dollar sign, it's going to find where is the DAVG node. Oh, there is no DAVG node. It will throw you an error. So here, the DAVG is a parameter of MaBoSS, and we are changing the parameter at the CC3D level. Okay, so in the delta notch config file, we have dollar sign DAVG equals 0, and we are going to use the CC3D integration, the CC3D MaBoSS integration to change this value depending on the delta expression of the neighboring cells. And then we have another parameter here, d underscore threshold. This is one we're going to set and leave. This is truly constant, not a this is a true parameter, not a variable parameter. And the threshold is basically the delta sensitivity of a cell. So if the external level of delta is above the threshold, the logic will be true. And if the expression of delta around the cell is below the threshold, notch is false. Sorry, the logic is false. And because delta activates notch on self, we have that if the logic is true, the rate up is some value greater than 0. And if the logic is false, it's 0. Note here that everything that is not a node, and here logic is not a node, there is a symbol before. In the case of a parameter, there is a dollar sign. In the case of a logic, in the case of a Boolean statement, there is an at symbol before logic. So if I have logic 1, logic 2, logic 3, all of them will necessitate this at symbol before the word logic. Okay? So small nuance of MaBoSS here. For node delta, so notch inhibits delta. So we have our logic equals notch. So I could just abbreviate this and remove this line, the logic equals notch, and just have rate up equals notch, and then 0 column 1, and rate down equals notch, 1 column 0. So if notch is true, the rate up for delta is 0, so delta does not go up if it's down. And if notch is false, delta goes up if delta is false, or if delta is down. These values here, these are probabilities or probability or rates. So every time you step the MaBoSS simulation, there is this probability of transitioning. So if logic is true for notch and the probability is 1, notch will deterministically go up. If you set anything below 1, so 0.1, there is a 10% chance it goes up. So you have an effective average upregulation time and an average downregulation time if you set this probability to be anything lower than 1. But basically, what you want to remember here is whenever you increase this value, the faster the node is going to go up or transition, the transition is going to happen. And whenever you decrease the value, the slower the transition is going to happen. Again, the configuration, you define the initial states of each node. To define that, you say notch.isState, isState, initial state, equals 0 or equals 1. And you define the parameter values with the dollar sign, name of the parameter equals, and then you can have any integer or float value. Now let's take a look in the CompuCell side. So this config should replace the antimony code entirely in the file. Eventually, yes, these two strings will replace the antimony code entirely in the file, yes. Let's take a look in the CompuCell side, how it will look like. There are two important changes. One is we have to import to random because we are using a random seed for MaBoSS. And this is the syntax for attaching a MaBoSS model to a cell. So you have your you have a cell, so you're, for example, looping over cells, and this is you give it a cell object, the cell you want to embed a MaBoSS model to. You have a model name. This is what you're going to use to refer to the model by saying cell.delta notch. This is how we're going to get the model, or cell.maboss.delta notch. We'll check the syntax later. We give it the model string and the configuration string variables. And then we define a time step and a time tick. The time step is how many steps you are going to iterate your MaBoSS simulation per Monte Carlo step, or every time you call the integrator. And the time tick is the time resolution of the solver. So if you increase time tick from 1 to 2, MaBoSS is going to use a finer time interval for checking the transitions. So effectively, and I can go in more detail into this, but it uses the Poisson distribution to recalibrate the transition rates, and then it uses a smaller dt for integration. Usually, time step is always one. If you change time step, you are going to change the time scale of MaBoSS. It will work on a different time scale than CC3D. So usually we set time step 1 and time tick you can vary depending on the resolution you are interested in, but usually we also use time tick equals 1. Question in the chat, in MaBoSS framework, do we have to represent each reaction as a separate node each time? What do you mean by each time? So to attach network models to cells, we're going to use this function, add MaBoSS to cell, and this is what each of these lines are doing. You give it the cell to which you want to attach the model, the name of the model, the variable that contains the model string, and the variable that contains the configuration string. Then the time step and the time tick, the seed. So you're randomizing the initialization of your MaBoSS model. And this is something you are going to use, for example, in the for loop, in the cell loop. In the start function, this is how you're going to embed a MaBoSS model to a cell. You loop over all cells, and you call add MaBoSS to a cell, where the model name, you give it a model name, but you have to give the variables where the string variables where you define your MaBoSS and configuration files. These are some of the syntaxes you're going to use. For example, to refer to a MaBoSS model, you type cell.maboss. And then the name of the model. This is exactly the same name as you defined over here. You can access the value of a node in a model by saying cell.maboss.myModel and then square brackets with quotes the name of the node. This is how you get if it's true or false. And then to change, for example, a parameter value, a parameter is not a node. So it has a little bit of an awkward syntax. It is cell.maboss.myModel, but then .network.symbol table, square brackets, the name of the parameter in quotes equals a certain value. And then we use this function timestep_MaBoSS to integrate all the MaBoSS models in the simulation. I'm going to address this question in the chat because I think it's important. It kind of determines our understanding level of MaBoSS. So the question is, every time you have a reaction, so a system of reactions, do you have to represent each reaction as a MaBoSS node, as a separate MaBoSS node? And the answer is no. You do have to represent each object or each variable as a separate node. So let's work with an example here. I mean, we are already doing that, but let me use a simpler one. Let's say I have a cell producing a protein, okay? So I have a reaction that is simply nothing goes to protein A. Okay, this is my reaction. How would I write this using ODEs? I would do something like this. Okay? Or sorry. constant. Okay. So a cell is producing a protein. I have one reaction and I have one protein. In MaBoSS, I would simply do nothing. It's the same structure, nothing activates A, but I would have like a rule for A. I would have node A, and then I have the upregulation rate being some constant. But I could have another variable. I could have a variable B, and I could have this B, for example, um, C times B, for example, without a reaction for B. I could represent B as a node, but there is no reaction for B. If I have a reaction for B, I still have two nodes. Um, if you have as like the point really is how many objects you have. So how many of these variables you have. But like of it's it is expected that for each variable of an ODE model you have one reaction. So I think in practice the answer is yes. You would have one node per reaction. Yeah, effectively the answer I think would be yes here. But if I want to be strict, I would say it is one node per variable, not one node per reaction. All right, so let's keep going. This is how the step function is going to look like. We do a loop over cells and we loop over all the cell neighbors. And then we scan for delta on the neighbor cells by getting the state of a delta node, of the delta node. There is a dot state modifier here to the node object so that we have a value for it. This is going to return a Boolean. That's why we have an integer here, converting it from a Boolean to an integer. And then we add this value, so we are summing the delta expression on the neighbors. And finally, we pass this Davg to the parameter of the MaBoSS network. So cell.mabos.delta notch dot network dot symbol table Davg, this is the parameter, Davg of our MaBoSS model equals the average delta expression around the cell. And I have these um, two other lines. They are not doing anything in terms of the model. These are just for visualization purposes to track the expression of delta notch in the cells. Finally, we are going to use the time step underscore MaBoSS function. This is how you call it, self.timestep underscore MaBoSS inside the step function so that every step we update all the MaBoSS models we have embedded to all cells of the simulation. Finally, go ahead and implement all those changes. So you have to substitute the Tellurium model with the delta notch model. You have to add the MaBoSS model to the cells. You have to scan the neighbor cells and sum the delta expression and do the average. You do that by using this command, neighbor.maboss delta notch dot state, and the name of the node in brackets. And then you pass this value to the MaBoSS network as a parameter. So there is a different syntax for that. And to use the tracking fields, we pass the state of the node to the cell dictionary, and then we'll be able to visualize the delta and notch expression of the cells in player. Question in the chat, I'm confused about how this gives us the average delta, not the total sum. Right. So I have this n counter here, and then I divide Davg equals Davg over the counter. In the Boolean framework, what does the threshold 0.1 signify? So the threshold equals 0.1. This is the sensitivity of the cell to delta level. So if the average delta level is above 0.1, which means if more than 10% of the cells around express notch, notch is going to play a role in that cell by uh, inducing notch expression. And if not, if delta expression is below 0.1, so less than 10% of the cells, you have delta not playing a role in the cell. So delta will not activate notch in the cell. So it is effectively the sensitivity to notch. Sorry, the sensitivity to delta. This is what the D threshold is. Maybe I should call it desensitivity. And for the next year's workshop, people have an easier time understanding the exercise. So my bad. However, I would like to leave a question to you, Aritra. And the question is, what is the equivalent delta sensitivity here in the Tellurium model? What parameter signifies the same? That's not an easy question though. So feel free to just finish the exercise and not bother with that. While people are doing the exercise, I think we can probably address this question. So here we have n prime equals dk over a plus dk minus n. Of course, there is a parameter multiplying here, so there is a b here and there is a c here. Okay, so I'm adding those in. Let me do k and delta. Delta for decay, k for the production rate. What happens here if I increase k? If I increase k, my notch level will increase. So like if this guy is this is a true false statement, but written with continuous equations, okay, continuous functions. This is a true or false statement. If D is very large, this is 1. This is 1 for D large, and this is 0 for D low, okay? So this guy is a true or false statement. If K is very, very large, what happens is notch. If this statement is true, so I'm going to say this is my delta at delta, okay? My logic. No, it's kind of an ugly name. The ds, my statement, my d delta statement. If my delta statement is true, is 1, k is going to bring notch to different heights of levels. So if I plot notch over time, I would have notch at different levels depending on k. Now, if my delta statement is false, no matter what k I set, it's always 0. Always 0, no matter what k I set, the notch over time. Because when I'm multiplying a number by 0, so doesn't it doesn't matter. Okay? So k determines the level of notch, but what determines whether notch is going up or down is this true or false statement over here. Now let's plot this true or false statement using this uh, plotter function called MyMouse. Delta, if delta is very small, this is 0, okay? If delta is very large, it is 1. And I'm plotting delta. Sorry, I'm plotting this function d to the k over a plus d to the k, depending on d. So it is something that it goes from here to here, and then there is something in between, okay? If k is very large, we have something like this, okay? If k is very low, we have something like this. Let's assume here k is equal to 2, so k will have a shape like this, okay? Sorry, d to the k over a plus d to the k will have this kind of shape. What determines the threshold? When after like what value separates what is low versus what is high here? It is this value here, right? This value in the middle of my Hill function is what determines what is low versus what is high. Or it's when I adjust this value that I am um changing the understanding or changing the effect of what is low versus and what is high. Okay, so by changing this parameter here, I'm by shifting this Hill function left and right is how I change what is low, what is high. And this parameter is A. The middle of the curve is A. So given this explanation, what parameter here determines the threshold? Is equivalent to the threshold? Is it K? Oh my God, I'm using K for both. Oh no, 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 no. No, no, no. Illegal. Illegal. Lambda. Is it lambda? Is it A or is it delta? Or is it K? Which one is the equivalent to the threshold in the MaBoSS model? Yeah, correct. A is the equivalent of the threshold. So you will change A from 0 to 1. So if you set A to a very low value, which is here, you'll have a different pattern than if you set 0.9. If you set A to 0.9, you should see a different pattern. And I can do that right now. So let me do, how was this before? Here I have, let me clean all this mess. Here I have delta as the isolated ones. Now I'm going, we're using Tellurium. Now I'm going to set it to 0.9. Well, still the isolated ones. I was expecting something different. Yeah, I mean the exact value might depend on these other parameters, but I think if I keep increasing, eventually the pattern has to change. Okay, I was wrong. Maybe I was wrong. Maybe it's not A after all. Maybe it is some combination of the other parameters. I'll put more thought into it after we do the exercise. So this is what you are going to see, and I'm going to launch the MaBoSS simulation now. Mm, MaBoSS. Question in the chat. One of the advantages of the Boolean network is that we often don't know what the precise parameters are to put in a differential equation. Yes, I listed that as one of the advantages. Don't probabilities less than one introduce similar ambiguities? So the problem is you have experimental data from the expression level of a protein. Usually you don't know the exact concentration, and usually you do have an onset time. Like in the first 2 hours, you don't see the protein, and after 3 hours, you start seeing the protein. And you can use this time parameter to infer your transition rate. So this information is useful to determine the transition rate. If you don't even have that, so for example, if it's an endpoint assay where they leave the system, the experiment running for 20 hours and then freeze everything and then evaluates, so there is no time lapse, then you don't have information about anything. Then you also cannot decide what is the rate. So you have the same problem of parameter non-identification. But you can already identify some parameters of your MaBoSS simulation even if you have just an onset time and a fading time. While if you're using reaction kinetic models, usually you need more information to determine the parameters. In a situation where we don't know what the precise values are, which ambiguity is going to result in a more useful model? Is the stochastic Boolean still simpler because there are fewer parameters to guess? Would a parameter search be simpler? Yes, a parameter search would be simpler in a MaBoSS model because it has less parameters. Yes. Although a continuous model instead of a MaBoSS model could still be more useful than a MaBoSS model. Okay? Even if you do not have identifiability for the parameters, if you can't identify the parameters. One example is MaBoSS networks struggle with delayed processes. And from my experience, ordinary differential equations handle those much better. So if you have a system that has, for example, an exponential evolution where it's very low for a very long time and then suddenly it spikes, ODE models represent this kind of behavior much better than MaBoSS. So even if you don't have the right, if you don't have literature information, experimental information to calibrate all your ODE model, it could still be more useful than a MaBoSS model. Usefulness is problem dependent. It depends on what you are modeling and what are your goals with that model. Do you want to predict something? Do you want to test if a certain experiment is informative or not? Do you want to test a hypothesis? Do you want to test a scenario? Do you want to run a perturbation? Depending on what you want to do and what is the problem you are working with. Are you modeling gene expression? Are you modeling cancer growth? You have usefulness will depend on each of these. So it's situational. Now, fewer parameters I can tell you for sure MaBoSS will have fewer parameters. Will the parameter search be simpler? For sure, MaBoSS search, parameter search will be simpler. Yeah, that's that's for sure. And if your MaBoSS model fits the data as well as your ordinary Boolean, sorry, your ordinary, oh my God, I'm mixing all the words possible. St Ordinary differential equation system, if both of them fit the data as well, you would prefer the MaBoSS model because it has fewer parameters, yes. But it could still be less useful if you want to test a drug that acts on a very specific process, like the decay time of a molecule, then MaBoSS, mm, more limited. How about when the number of nodes is large? With differential equations, I have had to limit the number of players in the network. Is there a point where the cost benefit shifts to Boolean? I would say yes. Yes, there is a point where it's more beneficial to use a Boolean stochastic network because of performance issues. If you are, especially if you are modeling very complicated large interactions with a lot of players, and for example, immune system, if you're modeling um, something very complicated as pathogen detection and activation of NF-kappa B, regulating all imaginable behaviors of the cell. I would say using a Boolean network would get you further because it runs faster than an ODE analogous. Although I am struggling with performance using MaBoSS, but it's not because Boolean stochastic networks are expensive. It's because probably there is an optimization issue with parsing between MaBoSS and CompuCell3D. I I sent an email to the devs complaining. Maybe we'll have a fix for that. But yes, eventually, theoretically, yes, there is a point where using Boolean stochastic networks is computationally more uh, computationally faster, yeah, than they're always faster, by the way, they're always faster than their analogous ODE models. However, if you have small models, small ODE models, and you care much more about like the onset, like the different levels of a protein through time, and the network is small, then it's preferable to go with an ordinary differential equation system. An example where Boolean stochastic networks fall short is, for example, let's say cell migration and actin polymerization. You cannot really have actin being true or false, can you? It's always there, but it has different behaviors, like it assembles, it disassembles. There is a non-set time where the cell polarizes and the cell depolarizes. It takes a time. So I would say using Boolean stochastic networks would not be appropriate for modeling something like actin dynamics. Oh yeah, and there is a histogram part where I am taking the number of cells expressing delta and the number of cells expressing notch, and I plot those in a histogram. Yeah, we have material for how to plot histograms in CC3D. You are welcome to check the slides later. So coming back to this, when you change the threshold value, so if you set the threshold to something like 0.1, you get delta as isolated cells. delta expressing cells isolated. And if you set it to something like 0.9, the delta will not be the isolated cells. Now the notch cells are the ones isolated. And if I launch the ODE model, this is what I see, delta as the isolated cells. However, I was expecting that if I increase it A, V equals 1. So they are all normalized. They all go from 0 to 1. If A is 0.5, I have um it is depending on B though. B is 100. I think the time scale is screwing up. Let me see what happens if because I tested A equals 0.01 and I tested 100. Let me try doing B equals 1 and see what happens here. Were you guys able to complete the MaBoSS simulation, the delta notch MaBoSS? Were you able to recover the patterns? Yep, there we go. Uh, Nihar is running the Antimony version, not to the MaBoSS version. Yeah. It is easier to control than the Antimony one, the Tellurium one. I'm struggling here. Try a couple of things. If I do this, B equals 1, A equals 0.01, I'm not getting any pattern. Ah, they all equilibrate. Huh. The equilibrate. Notch and delta equilibrate. You gotta be kidding me. Uh, there is a one there. Still equilibrating. Yeah. Yeah, if I keep going with this Tellurium model, I'll never stop. Yeah, that's it. I don't know if I had any extra exercises. Compare the histograms and the next step would be to couple a cell cycle model, but it is left as homework. So summary, high-speed and accessible version of your default ODE system. Everything is Boolean. Everything is true or false. There is no in between. All parameters are time rates and they're fast. That's it. That's the summary. You might find use for them. Question. I need to link the delta notch network to a reaction diffusion system. As in our system, the delta notch system works in the context of center biased FGF signaling, a pattern that self-organizes with reaction diffusion system involving Wnt and FGF signaling. Here, center biased FGF activity initiates center bias pattern of delta, okay, which is required for specification of a central cell in a cluster. Okay. What would be the best way to couple the Boolean network, the Boolean model? Oh, would it be best to couple Boolean model or differential equation? I think both work. Both could work fine. Um, if you are if you are modeling your reaction diffusion system externally to the cells, you couple them to MaBoSS just the way we are doing here, where you pass the concentration of some chemical as a parameter into the MaBoSS model. This is what I do in the model I work with, the which is a influenza infection model. Um, and then the concentration is going to alter the rates. This is very possible. And the patterning will emerge very quickly because of the MaBoSS, because of the Boolean stochastic network. If you care about the transient a lot, like the cell becoming delta and the cell becoming notch over time, because it has different behaviors in between, Tellurium, the ordinary differential equation approach is more suitable. But if you just care about getting the patterning and having an external molecule like FGF controlling which type of expressing cell is in the center of the cluster, and you don't care about um, the um, the um, the transient of delta and notch expression, then MaBoSS would work just fine. But it sounds like both would work, given your description. If your ODE system is very small, there isn't much of a difference between in terms of performance between using MaBoSS and Tellurium. But if your network is huge with 50 variables, then of course MaBoSS is going to run faster for you. All right, I will thank you, everybody, and launch the poll. Yeah, I would
Thank
say
you.
like if FGF concentration causes, I mean, if you are interested, for example, in getting the timing right, for example, I have an experiment showing a time lapse of this pattern developing, and I'm interested in calibrating my simulation parameters such that at the 20 hours mark I have this pattern. You have much more control of timing using ordinary differential equations. But if you are just worried about the steady state, the outcome, the final outcome, MaBoSS can do that. And it's going to be easy, much easier than using ODs. So that's another consideration.